Welcome back, ladies and gentlemen, to my Introduction to Mathematics course. Today we're going to talk about sets and maps. We already introduced sets and set notation very briefly before when we talked about logic, and we already saw some very important examples of sets, such as the number sets, the natural numbers n, the integer z, the rational numbers q, and the real numbers r. And we also learned about the empty set, which is a set that contains nothing at all. To keep this lecture self-contained, I will first quickly recall Cantor's definition of sets, the same one we already had before. And then we will explore operations on sets and properties of sets in more details. There will be quite a few proofs in this lecture, so put on your proof hat and get into the mood. And we will also introduce maps between sets as a means to compare sets and better describe their properties. Now, if you want to experience set theory firsthand, you too can become an element of a set, namely the set of my subscribers. So please like this video and subscribe to my channel to support me. Today's video has three parts. First, we review the naive definition of sets again. Then we will learn about operations on sets, which in a way mirror the logical operations we have learned before. And then we will learn about maps between sets and their properties. First, let's review the definition of sets in naive set theory. So, as you may recall, the theory of sets is a relatively new branch of mathematics, and it originates from the 1870s and is due to the work of Georg Cantor. And he originally defined sets using just natural language. But without any further refinement, this naive definition led to paradoxa. So it was eventually necessary to create a more refined set theory based on formal logic, and this was called the axiomatic set theory. But for us it is sufficient to use Cantor's definition of sets from naive set theory, which is the following. A set is a gathering together into a whole of definite distinct objects of our perception or of our thought, which are called elements of the set. We use curly braces to denote sets, so within these curly braces we write down the elements that the set should contain. We can do this in an explicit way, that is, we just list all the elements explicitly, like we do here. So if big X is our set, then 1, 2, 1, 3, 5, 7, 9, 11 are explicitly listed to be the elements of X. Or we can implicitly define a set by stating some property that all the elements in the set should have. So we can define a predicate. In this example, we could define the predicate Px, meaning X is an odd natural number less than 13. And then we would write within the curly braces that big X is the set of all elements X that satisfy this predicate P of X. And then this would be exactly the same set as this one. We use this notation to express that the element X is contained in the set big X, so this stylized E or epsilon here. And if X is not contained in the set big X, then we just use the same symbol but crossed out. And in principle, it is always the case that some object is either an element of the set or is not an element of the set, even though in practice it might be impossible for us to decide which one is the case. Also, it's important to note that the elements in a set are not ordered in any way, and they do not repeat. So note that these three sets all are the same. It doesn't matter in what order I list the elements, they are all considered to be the same set. And here it's possible to write down an element of a set repeatedly, but it still is contained only once in a set. So if I just write down the element 3 times, it doesn't matter, it's still only contained once here. Now, I already hinted that the naive set theory leads to some problems, and this is because it does not restrict which objects can be combined into a set. And this leads to several paradoxa, and possibly the most famous one I want to show you here. This is called Russell's paradox, and it is named after the great philosopher Bertrand Russell, who lived around the turn of the 19th to 20th century. And he made some very important contributions to the logical foundations of mathematics, among other things. And he formulated this paradox in 1901. And as I suggested before, this reinforced the need for an axiomatic theory of sets. So it showed that the naive set theory wasn't good enough. Now, this is the paradox. Let R denote the set containing all sets X, such that the set X is not an element of itself. Okay, that's maybe something you need to get your head around first, what is meant here. We have a set R that contains other sets as elements, and these sets should have the property that they do not contain themselves as elements. Now the paradox comes from the question, is the set R an element of R or is it not? Well, let's think about this. Assume that R is contained in itself, but then it does contain itself, but by definition of the elements of R, it should not contain itself. That is a contradiction. Now assume R is not contained in R, but then, by the definition of the set R, all the elements in R are precisely those that do not contain themselves, but that would imply that R does contain itself. And again, we have a contradiction. And there's no solution to this paradox, and this shows that it is a bit problematic if you just allow sets to contain completely arbitrary things. And such problems can be resolved by using a so-called axiomatic set theory, where we define sets through logical axioms, where an axiom is a statement or a proposition, if you like, that is taken to be true by assumption. So it does not have to be proved, but you just take it as a truth, and from the assumption that this is true, you can derive new facts through logical reasoning. Now, on this channel, or in particular in this current course, all the sets appearing can be derived from sets such as the natural numbers that can be constructed in axiomatic set theory. For example, to name two such theories, the probably most famous one is the Zermelo-Fraenkel set theory, or also the Gödel-Bernet set theory is a popular one. And because we can justify the existence of all the sets we're using here, it is actually sufficient for us to use the point of view of naive set theory. So going into axiomatic set theory here, that would amount to a whole course in itself. And I do not want to do this in this introduction course. So we stick with naive set theory, but rest assured that everything we do with sets here can be justified by axiomatic set theory. Now we look at operations on sets, and as I said before, these operations mirror the logical operations we have encountered in previous videos. First, something that may seem rather obvious. We say that two sets A and B are identical or equal, written as you would expect it, if A and B contain the same elements. Or more formally, if X is an element of A, if and only if X is an element of B. And if this is not the case, we write A not equal to B. So this means there exists objects that are contained in A but not in B, or the other way around, there's something in B that's not contained in A. A set is called a subset of another set, so A is called a subset of B if every element of A is also an element of B. This means X element A implies X element B. So here I have this little diagram to indicate this. B contains all these elements here, and A is a subset of B. It contains a few elements here which are all contained in B, but you will note there are some elements of B that are not contained within A. Now if A is a subset of B, we use this notation here, A subset B, or also this notation without this little line here. Now this little line here is supposed to indicate that A could be equal to B, so it's not excluded. But note that this notation here means exactly the same as this. It's just a convention. So it may be a bit confusing because these symbols are a bit reminiscent of the less or equal and the strictly less symbols we know from arithmetic, where those actually have distinct meanings. But in set theory, these two symbols here are used interchangeably. So please don't be confused by that. Now, if there is at least one element X in the set B that is not contained in A, then we say that A is a proper subset of B, which is the case in this little image here. And then we write A subset of B but not equal. So here we cross out this little line that would in this notation indicate the possibility of them being equal. Here we cross it out to say A is a subset but it is not equal to B. And if A is not a subset of B, so there's at least one element X in A that is not contained in B, then we write this. We write A with a subset symbol crossed out, B. So please do not confuse these two notations here. This one means A is a subset of B, yes, but equal? No, A is not equal to B. Whereas this one means that A is not even a subset. Now we look at the union and the intersection of sets corresponding to the logical and the logical or, as will become clearly here. If we have two sets A and B, then the intersection of A and B, written like this, consists of all objects X that are elements of A and at the same time elements of B. And this is called the intersection. Here in this little image it should be clear what is meant. So here we have the set B, here we have the set A, and there are a few things that are contained in both A and B, and this is what we call the intersection. And if the intersection is empty, that means if A and B do not have any element in common, then we say A and B are disjoint. So this is the case if A intersection B is the empty set. And the set A union B is the one which consists of all objects X such that X is an element of A or X is an element of B. It could be both, doesn't have to be both, but it has to be in A or in B. And then we call this set comprising these elements the union of A and B. So here in this image, the union of A and B would be all the dots you can see in both of these sets. And we can define unions and intersections for more than two sets. And we use this notation here, which maybe takes a bit getting used to. So let's say we want to have the union and intersection of k different sets, where k is a number greater or equal to. Then we can use this big intersection symbol and we count from 1 to k over our sets A1 to AK. So this notation basically means the same as this one here. And that means we have the set of all x, such that x is in the first set and in the second set and so on. And finally x is also in the last set, the kth set. And for the union we have the analogous notation. Here we have the big union symbol over all the sets A1 to AK, and this is the set that has all the elements x, such that x is contained in A1 or in A2 or in any of the following sets up to AK. An example with some sets that we should be familiar with now. We have our number sets, the natural numbers beginning at 0, 1, 2, 3, 4, 5 and so on, is of course a subset of the integers. The integers is a bigger set in the sense that it contains elements that are not in n, so it has -1, -2, -3 and so on. This again is a subset of the rational numbers q, where q contains the fractions of all the numbers here, and q in turn is a subset of the real numbers. And you might recall from a previous video that there are real numbers that are not contained in q, for example the square root of 2, and so q is in fact the proper subset of R. So more precisely we could write it like this, using this subset but not equal notation. N is a subset of the integers but not equal to them. The integers are a subset of the rationals but not equal to them. The rationals are a subset of the real numbers but not equal. And we can also say that the integers are not a subset of the natural numbers because they contain elements that are not contained in the natural numbers. And again, I want to emphasize the difference between those two symbols. So I hope comparing these examples here might make it clear what the different meaning is. Let's look at an elementary example. Here the set A, 1, 3, 5, 7, 9, 11, so the odd numbers up to 11, and the set B consisting of some multiples of 3, 3, 6 and 9. First we observe that A is not a subset of B, which is quite clear because there are several elements in A that are not contained in B. 1, 5, 7 and 11 are not contained in B, so A is not a subset of B. Also you can argue that B is not a subset of A because the element 6 that is in B is not contained in A, so neither one is a subset of the other. Then we can form the intersection, and there we look at those elements that are contained in both sets, and this will be only 3 and 9, which are contained in both. The other ones from A are not contained in B, and the number 6 in B is not contained in A, so they're not in the intersection. And finally the union, where we just take all the elements together that are in A or in B, is 1, 3, 5, 6, 7, 9, 11. So we notice that 3 and 9 are contained in both sets, so we don't have to count them twice because we don't count elements twice in sets. So these are all the elements in A, in addition to the element 6 here that comes from B. and that is the union of the two elements. And another example that you maybe have to think about for a moment. If X is any arbitrary set, then it is true that the empty set is a subset of X. Now, to understand why this is true, we have to think about the formal definition of a subset. For empty set to be a subset of X, it must hold that every element of the empty set must be contained in the set big X. Now, the empty set does not contain any elements, so this requirement is trivially true for all elements of the empty set, because there are not existing any elements in the empty set. It is just not any requirement at all. It's an empty condition, if you like. And that's the reason that the empty set is a subset of any set. Now, given two sets A and B, we can form the complement of A in B. So this corresponds logically to the negation. This is written like this, B backslash A, and consists of those elements that are contained in B, but at the same time are not contained in A. For this notation, it does not matter whether A is a subset of B or not. So if A is a subset of B, however, then we can use this special notation here, A C, so C standing for complement, instead of B backslash A. Now, this notation only makes sense if it is clear what the ambient set B is supposed to be. So this notation is always clear because it explicitly refers to where we take the elements from and where we forbid the elements from. And this notation is maybe a bit shorter, but can only be used if it's clear which ambient set B we are referring to. And here I have a picture for this. So this box, everything in there is the set B. Then we have this subset A. So here we have the situation where A is in fact a subset of B, and all the elements of B, which are indicated in red here, that are not contained in A, form the complement of A within the set B. Now we have Cartesian products. So if two sets A and B are given, then we can form a new set A times B. So we read this times as like a multiplication, but note that we don't really multiply anything here. A times B is the set of these pairs AB, where the first entry of this pair is taken from the set A and the second entry is taken from the set B. And this is called the Cartesian product. So this is a set of ordered pairs whose first entry is taken from A and whose second entry is taken from B. Now here we can't, within this pair, we can't change the order if A and B are different sets. So it's important to note in which order we write down the sets in this Cartesian product. Yeah, and as I said, the symbol here, this times multiplication or cross symbol, does not mean that we multiply anything. It is merely suggestive notation, and as we will see later, it comes from the fact that if A and B only have finitely many elements, then their Cartesian product will have precisely A times B elements. So, or then the number of elements in A times the number of elements in B will be the number of elements in this product. And that's why we use this multiplication symbol here. One example that you might know from geometry is that the points in the plane can be described by coordinate pairs x and y. So we have an x-axis and y-axis, and this pair of coordinates describes how far we have to go along the x-axis, and then how far we have to go up or down the y-axis in order to get to one uniquely described point. And so this two-dimensional plane is the Cartesian product of the real numbers with itself. And we usually write this as R2. So instead of R times R, we write R2. It's a bit shorter. And we can define the Cartesian product for more than two sets. So if we have n different or not different sets, I can write A1 times A2 times times AN. And these are the sets that contain ordered sequences of n elements, where the ith element in the sequence is taken from the ith set in the product. And such an ordered sequence of n elements is called an n-tuple. Okay, so the Cartesian products of the sets A1, A2 up to AN is a set of n-tuples where the first entry is taken from A1, the second entry is taken from A2, and so on, and the last entry is taken from AN. If we are in the situation that all of these sets are the same, so A1 is equal to A2, equal to A3, and so on, and equal to AN, then we can simply write A to the power of n for this Cartesian product. That's similar to what we did here for the real coordinate plane, where we write R2 instead of R times R. Let me give you an example, a bit arbitrary, but I hope it makes the concept clear. We have two sets, X and A. X contains the two numbers 1 and 2, and A contains the card suits, so heart, spade, diamond, and club. And so the Cartesian product of these two sets contains all the ordered pairs where the first entry is taken from X, so it's one of these numbers, and the second entry is taken from A, so one of these symbols here. And if you go through all possibilities, you get this set here. So the first pair has the entry 1 taken from X and the heart taken from A. Then again we have entry 1, and now we have spades taken from A, 1 and diamond, 1 and clubs. And then we have all the combinations that have the 1 in the first entry. Now we take the combinations that have the second element 2 in the first entry. And that is these ones here. And note that X contains 2 elements and A contains 4 elements. And the product contains 2 times 4 elements, so 8 elements. And that's what I mentioned before. If there are finitely many elements, then the product will have the product number of elements from the original 2 sets. And that's where this surjective notation comes from. Now, a little exercise for you to get used to the set operations. So pause the video for a moment and write down these sets for the given following sets. So here we have the numbers -1, 1, -2, 2, -3, -4, 4 in the set A. B contains the numbers 1, 2, 3, 4, 5, 6. C contains all the numbers to n, where n is from the natural numbers. So these are the even natural numbers. And yeah, the set D is maybe a bit mysterious here. It contains 2 Hebrew letters, the Aleph and the Bet. So this is a set just containing 2 symbols, but that's a perfectly legitimate set. And with these sets, write down the union of A and B, the intersection of A and C, the intersection of B and C, then B without C, so the complement of C in B. And here we have a Cartesian product of 3 sets, the first one being D, then the intersection of B and C, which we have computed here, and then again D. And you're supposed to form all the elements in this Cartesian product. So pause the video now and try to do this. So I hope you gave it a try, and here's the solution. For the union of A and B, well, we have all the elements of A and all the elements of B. We don't take any of them twice, so the elements 1, 2, 3, 4 of B already appear in A, so we don't have to take them twice, but the elements 5 and 6 do not appear in A, so we have the elements of A and the two elements 5, 6 of B that do not appear in A. Then we have the intersection of A and C, so A, these numbers, and C, the even, not integers, natural numbers, so we do not take negative numbers here. So the negatives are all gone, and the only even natural numbers appearing in A are 2 and 4. So A intersection C is just this set. And similar for B intersection C, we take the even numbers that are contained in B, that's 2, 4, and 6. And B without C, the complement of C in B, so that's those elements in B that are not in C, that are not even numbers, and these are of course the odd numbers contained in B, that's 1, 3, and 5. So we get this set. Now the last one, that's a bit of work. So we have a Cartesian product of 3 sets. The first entry taken from the set D, so it has to be one of these two symbols here, Aleph or Bet. The second entry taken from B intersection C, so it has to be one of these 3 numbers, 2, 4, and 6. And now the third entry is again taken from this set D with Aleph and Bet in it. So we have to form all the combinations of one of these two symbols in D, one of the 3 elements in B intersection C, and again one of the 2 symbols in D, in order to get all the elements in the Cartesian product D times B intersection C times D. And I did this here. You can actually check that these are all the possibilities. So I always took one of the 2 symbols, Aleph or Bet, in the first entry. Then in the second entry, it's one of these 3 numbers here. And in the third entry, it's again one of the 2 symbols, Aleph or Bet. And if I try all the possible combinations, I come up with this set. Now, we're going to study some laws for sets, and first I prove this little lemma here. And by a lemma I mean an auxiliary theorem that is often used in proofs of other theorems, but is not always such an interesting statement in its own right. So some people call a lemma a trick I used twice. So it's a helpful result, but not necessarily something that you would deem as of utmost importance in mathematics. And this one is a very straightforward statement. So if we have 2 sets A and B, then A being equal to B is equivalent to saying that A is a subset of B and B is a subset of A. This may seem pretty obvious, but I still want to give you a proof. So it provides you with the following strategy for proving equality of sets. If we wish to prove that A and B are equal, so we want to prove this, then we can split this into 2 steps by first proving A is a subset of B and then proving that B is a subset of A. So this is similar what we did for proving equivalences, where we could split it into proving the 2 implications that the left-hand side implies the right-hand side, and that the right-hand side implies the left-hand side. And it's completely analogous to that with these sets. And the proof is very simple, maybe trivial to you, but I think it's a good opportunity to see that even seemingly obvious claims have to be justified. So first I prove in this equivalence that we claim here the direction from the left to the right. So I assume that A is equal to B, so I assume this is true, and I want to prove that this is true. Now if this holds, then, well, A is clearly a subset of itself, which is equal to B. So A is a subset of B, and B is a subset of itself, which is equal to A. So B is a subset of A. And yeah, that's it. For the other direction, I now assume that A is a subset of B and B is a subset of A, and I want to prove that they are equal. So suppose every element of A is also contained in B, that is this one, and at the same time every element of B is also contained in A, that is this one, and both of them should be true by assumption now. So this means, in other words, that X in A implies X in B, and X in B implies X in A. But this means nothing else but X in A is equivalent to X in B, which means that A is equal to B. Okay, let's look at this again. Here we have an implication, X in A implies X in B, and here we have the implication of the reverse order of statements, so X in B implies X in A. And remember from logic, if we have that the first statement implies the second, but also the second statement implies the first, then the two statements are equivalent. So X in A is equivalent to X in B, but this is by definition just the same as saying the set A is equal to the set B. So by this we have proved that if these are true, then A is equal to B. Let's look at some more properties of sets now. Now we look at properties for the intersection and the union. I take three sets, A, B, and C now, and the following hold. We have a commutativity law, which states that A intersection B is the same as B intersection A, and also that A union B is the same as B union A. We have an associativity law, which means that we can move parentheses if we have intersections or unions of multiple sets. So if we take the intersection of A and B first, and then take the intersection of that with C, that's the same as taking the intersection of B and C first, and then taking the intersection with A. And also, if we take the union of A and B first, and then the union of C, that's the same as taking the union of B and C first, and the union of the resulting set with A. And then we have the distributivity laws for expressions that involve both unions and intersections. So if we first take the union of B and C and intersect that with A, that's the same as intersecting B and A and C and A and taking the union of those. And also, if we take the intersection of B and C and of that the union with A, that's the same as first taking the union of A and B and the union of A and C and intersecting the two. And the proofs of these statements essentially follow from the corresponding properties of the logical operators and or, the logical and the logical or. And proving all these properties in this lecture would take too much time, but for illustration I will just prove the last distributivity law here as an example. And the proofs for the other statements can be done in a very similar way. So the proof of this distributivity law, A union, in parentheses, B intersection C, equals A union B intersected with A union C. And we use the idea from this lemma 7 that we just had to split the proof for the equality here into two proofs for inclusions of sets. So what I will prove is that this set here is a subset of this one, and then I will prove that this set here is a subset of this one. First, I go from left to right, so I look at this set and I want to prove that it is contained as a subset in this one. So an element X is contained here if X is an A, or X is contained in the intersection of B and C. So one of these must be true if X is an element here. So first we assume that X is contained in A. In particular, this means that X is an element of A union B, because the union of A and B of course contains A. So every element of A is contained in this bigger set that contains A. And by the same reasoning, X is contained in A union C. But this means, if X is contained here and X is contained here, that X is contained in the intersection of A union B and A union C, as required. So it is contained in this part here. So this proves the first inclusion for the case that X is an element of A. Now we assume that X is an element of B intersection C, which means that X is contained in B and at the same time X is contained in C. Then in particular, X, because it's in B, is contained in the union of A and B, and X is contained in the union of A and C, because it's contained in C, so it's in particular contained in this bigger set that contains C. But this also means that X is contained in A union B intersected with A union C, okay, because it's contained here and it's contained here. So also in this case we see that X from this set is contained in the right hand side. And now this reasoning holds for all elements contained in A union B intersection C, so all elements from the left hand side. So it follows that A union B intersection C is a subset of the right hand side, a subset of A union B intersection A union C. So this is one half of the proof, and now we prove the inclusion in the other direction. We now prove that this set is a subset of this one. So suppose X is an element of A union B and an element of A union C. If X is an element of A, then X in particular is an element of A union B intersection C as required. So because the set A is of course contained in its union with any other set, so in particular if X is an A, then X is contained in this set. If X is not in A, so X satisfies this, but if X is not in A, then X must be in B and X must be in C. Okay, because it's in the union of A and B, but if it's not in A, then it must be in B. And similarly here, if it's not in A, it must be in C. So X not in A means X is in B and X is in C. But this is just another way of saying X is an element of the intersection of B and C. And in particular, X is then an element of the intersection of B and C union with A. And again, this holds for all elements x from the set on the right hand side here. So it follows that A union B intersection A union C is a subset of A union B intersection C. And what we've done now is we've shown the two inclusions, and with lemma 7 it follows that the two sets here have to be identical. So we've proven this set equality. Now we look at some properties for set complements. So A and B are sets, and then the following holds. The complement of A in A is the empty set. That's easy to believe. Second, the union of the intersection of B and A with the complement of A and B is precisely the set B. Intuitively, we can say that we take the elements of B that are contained in A, throw them together with all the elements of B that are not contained in A, and because every element has to be either 1, we get the full set B. Then, using this complement notation, if A is a subset of some other set B, then the intersection of A and its complement is the empty set. Very similar to the first statement. And finally, the complement of a subset of B is the subset A itself. Okay, so taking the complement 2 times just gives you back the original set. Again, it would be too time consuming to prove all of them, even though the proofs are maybe a bit shorter than for the previous laws. So I will only show the first two. The first one is very quick. So if A is an element of A, but also A is not an element of A, we obtain a contradiction. Can't have both at the same time. So there is no object A that satisfies A being in the complement of A in A, and hence the complement of A in A must be the empty set. It's a set that does not contain any object, because no object can satisfy this contradiction. For part 2, we use logical expressions for these sets here, and then we can show this equality by forming equivalent expressions. So here I do not use this trick of first showing that this is a subset here and then showing that this is a subset here, but I can do this simply by manipulating equivalent expressions. Okay, what do we have here? B intersection A union with the complement of A and B. So this is a set of objects B such that, corresponding to the first part, B is in B and B is in A. Union, or corresponding to the second part, so it's this, or B is in B and B is not in A. Now, using the rules for logical expressions, we can rewrite this as those elements B that satisfy B is in the set big B and B is in A or B is not in A. But of course, this is just a negation of the first part, and with a logical OR, having some proposition and the negation of the proposition, that will always be true. So basically what we have here is B contained in big B and true, and this just reduces to B element big B. So this set here turns out to be just those objects B such that B is contained in B, and that's nothing else but the set B itself. Yeah, and for parts 3 and 4 you can do similar reasoning as for the first part. I'm not going to show this. Next we have De Morgan's laws for sets, and if you did the first homework you might recognize this from the corresponding formulas for logic. So we assume that A and B are both subsets of some given surrounding set X. And then we have the following rules for the complements of A and B in X. A complement union B complement equals the complement of the intersection of A and B. And analogously, A complement intersection B complement equals the complement of the union of A and B. And I will only prove the first formula here, because the second one is proved in a very similar way. And if you really want to, you can do this as an exercise. But I think if you see the first proof, it's pretty clear how you would go about the second one. Now, recall this notation. A complement just means the complement of A in X. So those elements in X that are not contained in A. Now we look at some element little x that is contained in the set big X, and this will be assumed throughout. And now suppose that X is contained in the union of the complement of A in X and the complement of B in X. So this is this side here. We assume X is contained in the left-hand side. So that means X is not in A or X is not in B. It has to be contained in one of these two sets, and those two sets are defined by X not being in A or X not being in B, respectively. And this is equivalent to X not being contained in both A and B at the same time, which means X is not contained in the intersection of A and B. It could be in A, but then it can't be in B, or it could be in B, but then it can't be in A. So it can't be in both, it can't be in the intersection. And by definition, this means nothing else but X being contained in the complement of the intersection of A and B within big X, or this in the short notation. So it follows that X being contained in this set is equivalent to X being contained in this set here. And thereby these two sets are identical. And an alternative proof would use De Morgan's laws from logic, which you discovered in homework 1. And you could try to do it using these laws. It's maybe a bit clearer then. Now, it's your turn again. Pause the video for a few minutes and prove for two sets X and Y that the union of X and Y intersected with the set Y just gives you the set Y again. And you can use the distributivity law from proposition 8 for this. And please give it a try. All right, let's see how we do this, and you can compare your solution approach to mine. So we use the distributivity from proposition 8 to rewrite our set from the left-hand side, X union Y intersected with Y, as the union of X intersected with Y and Y intersected with Y. Now, of course, if I intersect a set with itself, it's just the original set again. So I could replace this one just by Y, and that's what I do here. So our original set is the same as X union Y, X intersection with Y, sorry, X intersection Y, union with Y. But now, comparing it with the right-hand side, we see that Y is a subset of Y union X intersection Y, because Y is a subset of the union of itself with anything. But also, x intersection y is of course a subset of y. So this whole thing here is a subset of y union y. And the union of a set with itself is of course the set again. So we've seen here that the right-hand side is a subset of the left-hand side, because we saw that this is identical to the left-hand side, but also that the left-hand side is a subset of the right-hand side, y. And by our principle of splitting the equality proof into the two inclusions, we find that the two sets must be equal. And this proves this claim here. Now we will fill our set theory with life by introducing maps between sets. So let x and y be two sets, and a map, or also called a function, f from x to y, is an assignment of a unique element y in the set big Y to each element little x in the set x. And this unique element y that gets assigned to x is denoted by f of x. And to declare such a function, we use the following notation. First the name f of the function, then the set x mapping to y. So x is the set where we take our input values from, and y is the set where the output values are taken in. And then we describe how the particular map works. So here x is the input value and it gets mapped to f of x. And if you had a concrete example of a map, then here you could have an explicit expression where this input value x gets mapped to. We say that the set x is called the domain of the function f, so this is where the inputs for f are taken. And the set y is called the codomain of f, so the codomain is where the output values are taken in. And now, if you're a very formal mathematician, you might complain about the word assignment in the previous definition, because this is not really a precise term. So if you want a more formal definition, let's look at one. A partial map f from x to y is a triple fxy, where x and y are sets, and f is a subset of the Cartesian product of x and y, with the following property, that for all elements x in the set big X, there is at most one element y in the set big Y, such that the pair xy is contained in this subset f of the Cartesian product. Then this f is called the graph of the partial map. And if there's no chance of confusion, so if the sets x and y are fixed, then we simply write f for the whole partial map. So we won't list the triple here, but we will simply write the symbol f for this partial map. The domain of definition of the partial map, DOM-F, is the set of all x in the input set big X for which there exists an output value. So for which there exists an element y such that the pair xy is contained in this subset f in the graph of the partial map. The image of the partial map is the set imf, which consists of all elements y in the output set, such that there exists some element x in the input set, such that the pair xy is contained in the graph of our partial map. And now we can define what a map is. Then a map f from x to y is simply a partial map whose domain of definition is all of x, or DOM-F equal to x, in other words. So Was that better? Good. So given all of this, it's probably more convenient to simply stick with saying a map is an assignment of elements from one set to elements of another set, and this is what we will be working with from now on. Let's look at some examples. So here we have a very familiar example, the standard quadratic function. And this is a map f from the set R, from the real numbers, into the non-negative real numbers. And the assignment is simply done by sending the value x to the value x squared. And you know this from school probably. You can plot such a map by drawing its graph. So here this axis, the x-axis, is taken to be the input domain, the domain of the map f. And yeah, it assumes values along this graph, and here the y-axis that corresponds to the codomain. That would be the non-negative real numbers here, where the values of the map are assumed. And we can form something similar, but instead of real numbers we input integers, and our output numbers will be in the natural numbers. But we use the same prescription for our map. So again we map x to x squared, but now for input we only use the integers, so the red dots indicated here on the real number line. And here the blue dots are the function values that are assumed for these particular integers. Now if x is an arbitrary set, we can define the identity map on x. This is a rather boring map because all it does, it takes an element x and just maps it to itself. So it doesn't do anything. But still, it's a quite helpful concept to have this identity map. It will appear many times in mathematics. And it's certainly not the last you've seen of it here. Another very simple type of maps is the inclusion map. So if y is a subset of x, then we can define the inclusion map of the subset y into x, simply by mapping any element of the subset again to itself. So it's a bit similar to the identity, but here we have a smaller input set than our output set is, but each element gets mapped to itself. So we think of this inclusion map as simply taking the subset and embedding it into its surrounding set X. We can view multiplication as a map. So for example, multiplication of integer numbers is a map from the Cartesian product z times z and mapping again into the integers, where we take a pair of integer numbers x, y and map it to their product x times y. And of course, in the same manner, we can view multiplication of rational or real numbers as a map. Now here we have an example of something that is not a map. And I make the following, assignment in fat quotes. F from the rationals to the rationals, taking a fraction p over q and mapping it only to its denominator 1 over q. But this is not a map, and I'll leave it to you to figure out why that is. You can write it in the comments if you like. But this is a problematic assignment, and you will find that we cannot define a map in this way, even though just formally it looks like one. And now a map that does not just involve sets of numbers. For example, if U is the set of US citizens and SU the social security number for a particular citizen, then this defines a map S from the citizens into the integer numbers, or the natural numbers to be precise. I don't think they are negative social security numbers, by mapping each citizen to its social security number. Now something like this might work for other countries, of course, if they have unique social security numbers for every single citizen, but I don't think in every country this is the case. Here's a bit of a different example of a map now. We look at the plane R2 and we look at rotations in the plane. So if R alpha denotes a rotation in the plane by an angle alpha about some point in the plane, then this is in fact a map. So R alpha maps the plane to itself. So every point in the plane gets mapped to another point in the plane by taking this point and mapping it to the point where it gets rotated to. So I have this image here to clarify this a little bit. So here the rotation is taken about the coordinate origin, and I took alpha to be pi over 4, so this corresponds to a 45-degree angle. And now look what happens to some of the points. So I took a few points here and showed where they get mapped to. The point with coordinates 1, 0, so this is just, you go one step along the x-axis, 0 step up the y-axis. It gets rotated by 45 degrees about the origin, so it gets mapped to this point here. And similarly, if we go a step further, the point with coordinates 2, 0 also gets rotated about the origin by 45 degrees, so it gets rotated to this point here. And now a different point on the y-axis, for example, with coordinates 0, 3 gets rotated here, again by a 45-degree angle. So if we connect this back to the origin, you would see there's a 45-degree angle between the y-axis and the connecting line. And here we have a point on the negative y-axis, 0, minus 1. It gets rotated to this point here by 45 degrees. And you could similarly think for every single point in the plane that it gets rotated in a similar manner about the origin by 45 degrees. So these are just a few sample points that I picked to indicate how this rotation map works. Then a particular kind of map is where you use either the natural numbers or some finite set to enumerate elements of a set. So if I have a map from n, or from the numbers from 1 to n, into some set x, I can think of this as enumerating elements of x. So for example, a sequence of real numbers is a map that goes from the natural numbers into R. So I call this A. And for sequences, usually you use a certain index notation, this one here. So you write AK in parentheses and indicate that K is taken from the natural numbers. And yeah, this is the image of the map A, which consists of all the real numbers that are hit by this map A if we plug in any natural numbers. And we think of these numbers as appearing sequentially, one after another, being ordered by the order of their natural number input values. That's why we call it a sequence. So we think of A0 being the first element, A1 the second, A2 the third, and so on. And a similar construct you might know from geometry, where we use vectors to describe points in the plane or in space. So a vector is a tuple of numbers that corresponds to the coordinates of a point. And we can interpret such a vector as a map, V, from the set 1, 2, 3 into space, into R3, where for each index we assign the coordinate along the x, y, or z axis to this index. So we use this vector notation for such maps, V, is v1, v2, v3, and so this is the value of the map v for index 1, this is the value of map v for index 2, and this is the value for index 3. And so these three tuples containing the coordinates of a point in space are also maps in this sense. Now let K be any set, and a map from the Cartesian product of the set of the numbers from 1 to m with the set of the numbers from 1 to n into K is called an m by n matrix with coefficients in the set K. And usually we write it in such a rectangular scheme. So instead of writing A of ij, where I would be taken from this set and j would be taken from this set, we usually write A index ij, so we use the small letter corresponding to the name of our matrix. And this we call the coefficients of the matrix. So in this rectangular array here, we write the function values of this map A, taking one index here and one index here. So actually the first index is the row index. You see this changes 1, 2, 3 up to m. And the second index, the second input value j, is the column index. So for a given row we have the columns from 1 up to n. And in this way we can interpret matrices also as maps from these counting sets into the set of coefficients. Sometimes we are given a map f from a set x to a set y, but it would be more convenient for us to only study the map f on a subset of x. Let's call it w. For this we have the following definition. If f from x to y is a map or even a partial map, and if w is a subset of x, then we can define the restriction of f to w, well, by simply looking only at input values taken from the set w, but mapping them to their usual values f of x. And we write this restriction in this way: f with a bar index w index the subset that we're restricting to. Okay, so we do nothing but ignore a certain part of the input domain for our map f. And if f is a partial map, then restricting this partial map to its domain of definition will turn it into a map, into a proper, decent map that is defined on everything that we plug into it. And this is immediate from the definition of the domain of f. Now, given a map f from a set x to a set y, we say that the image, or sometimes it's called the range, of the map f is the following set. F of x is the set of all the elements in the set y, such that there's some element in x that is being mapped to y by the map f. So you could say it's the set of all possible output values if we try all possible input values for our map. And another way of writing this is it's a set of all elements f of x for x being taken from the set big X, and this is of course a subset in the codomain y. And I will also use the notation imf for the image of f. The notation renf for range is also common, but I'm probably not going to use this one. And here I try to illustrate this with this image. So we have x, our input values, y, the output values, f mapping elements of x to y. And all the values that elements of x get map 2 are contained in this image set. So we see there are some elements of y that are not hit by any of the arrows, so no element of x is mapped to any of these elements, but only to the ones within this image. And as this picture already shows, in general, the image of f is not all of y. So in general, you have to expect there are elements of y that are not hit by any element of x under the map f. And in a way, the converse of the image is the following. Again, we have our map f of x to y. And for every subset in the codomain, let's call it y0, the subset, we can look at the pre-image of this subset, and we denote this by f to the -1 of y0. And this is a set of all x's in the domain of f, such that this x gets mapped into the subset y0. And this pre-image is a subset of the domain f. So it's a subset of the input set. And we simplify the notation a little bit if we look at the pre-images of single elements. So if the subset y0 contains only one element, then we simply write f to the -1 of y instead of f to the -1 of the set containing y. Again, I hope this image here clarifies this. We have the map f from x to y, and I pick a subset y0 of y. This is not the whole image of x, it's just a subset. And the pre-image consists of all the elements in x that get mapped to elements in y0. So the red elements in x here are the only ones that get mapped to blue elements in y. So these make up the pre-image of the set y0 here. Let's look at some examples. Again, I look at the quadratic function defined on the integers mapping into the natural numbers. And for example, if I take the element 4 in the natural numbers, then its pre-image consists of the numbers -2 and 2. Why is that? Because if I square -2 and if I square 2, if I plug them in here, I get 4. So these are the two values in the integers that get mapped to the value 4 under this map here. For example, if I look at the value 3 in the natural numbers, then the pre-image is actually empty. There's no element in the integers that gets mapped to 3 if I square it. So the number 3 has no square root in the integers. Now if I'd looked at real numbers here, that wouldn't be a problem. I would get proper pre-images for 3, but if I restrict to the integers, then I do not have any integer that squares to 3. So that's why we get an empty pre-image for 3. If we look at the quadratic function on the real numbers, mapping the reals into the non-negative reals, then the pre-image of any positive number consists of its square root and minus its square root. Okay, so for y larger 0, f to the -1 of y is a set containing minus square root of y and plus square root of y. And if we look at the pre-image of 0, then we simply get the set containing 0. So 0 is the only element in the non-negative real numbers that has only one element in its pre-image. Every other one has 2 elements in its pre-image. And here's a more complicated but probably also more interesting example. Let's look at the sine function. I hope you've seen that in school at some point. The sine function maps the real numbers into the real numbers. simply taking a value x, mapping it to the sine of x. But the image of the sine function is simply the interval -1 and 1. So it doesn't cover the full range of real numbers, but it oscillates between 1 and -1, as you can see in the graph here. And now I ask, what is the preimage of the interval from 0 to 1? So I ask, what is the preimage of this interval on the y-axis going from 0 to 1? So I look for all the real numbers that, if I plug them into the sine, will take a value that lies between 0 and +1. And I've indicated this here in the graph a little bit. I hope it's clear to see. These are the red intervals. These make up the preimage. Because whenever you're in one of these red intervals, your sine takes a value between 0 and 1. And whenever you're out of it, it takes a value below 0, down to -1. So these ones I'm not interested in. I just want the red ones. And how can I write this more formally? Well, it's the union of all these red intervals, and they go up to infinity. And it's always the union of an interval going from an even multiple of pi to an odd multiple of pi. So for example, if we look at n equal to 0, then we take the interval from 0 to 1 pi. The next is an interval from going from an odd multiple of pi to an even one. Those ones are not included here. But the next interval that comes in is for n equal to 1, where we have 2 pi here. And the interval from 2 pi up to 3 pi. So that would be this bit here. And similarly, we have it in the negative numbers. And this goes up from -infinity to infinity. Next, we get to know some very important properties that help us characterize maps and eventually also sets between which the maps act. This is, from experience, a bit difficult for beginners, but I hope with the examples and the pictures I show you, it will be easy to understand. So, if a map f from x to y is given, it is called injective, or also one-to-one, if no two distinct elements of the input set x are mapped to the same output value y. Or, somewhat more concisely, if f of x1 equals f of x2, then x1 must equal x2. So look at this example here. We have our input set x and our output set y, and all input values x are mapped to different output values. So no two arrows go to the same output value y. And if that is the case, we call this function injective. The next property, f is called surjective or onto, if for every element y in the codomain big Y, there exists some input value x in the domain that gets mapped to y by our map f. So this is the situation here. We see that every element in y gets hit by an arrow. So for every element in y, we can find some element x here, such that f of x equals this y. Now, this was not the case here. Here we had certain elements where we had no arrows going to them, but here everyone has an arrow going to it. However, this one, for example, is not injective. We have these two elements mapping to the same dot over here. So this is a surjective map, but not an injective one. Whereas this one is injective, but not surjective. And finally, if we combine the two, f is called bijective if f is both injective and surjective. And if a map has any of these three properties, then we shall also call this map an injection, a surjection, or a bijection accordingly. Let's look at some examples. So first the integer quadratic function again, mapping the integers into the natural numbers by mapping x to x squared. This is not an injective map because if we take minus x in the integers, that maps to the same as x. So for all non-zero integers, we have two distinct values that map to the same output. It is also not surjective because, just as one example, there is no input value x in the integers that would get mapped to the natural number 2. So 2, even though it's a natural number, is not contained in the image of f, so it's not surjective. F is not surjective. If we look at the real quadratic function, it's still not injective for the same reason as we gave in the first example. But this one is actually surjective if we take the non-negative reals as the image. Because for every value y strictly greater than 0, we have y being f of the square root of y. So every positive y is in the image. And of course, the value 0 is f of 0. Now if we restrict this f only to the non-negative real numbers, then it also becomes injective because this argument from up here does not work anymore because we excluded all the negative numbers. So then it's injective and surjective, and in that case the restriction of the quadratic function to the non-negative real numbers is bijective. Now our identity map for any set x is injective and surjective, which is easy to see because the identity of x is just x, so any x is contained in the image of the identity map, hence it's surjective. And also if we have the identity of x and the identity of y, then they're just x and y, and they are distinct from one another if the elements x and y are distinct from one another. So the identity is bijective. And a rotation in the plane is also bijective, which, well, geometrically it's easy to see. I'm not going to formally prove this because we don't have the time to properly study rotations here, but I'm sure in some course in the future that will eventually happen. If we're given two maps that are suitably compatible, we can compose them. So what does this mean? If I have a map f from a set x to y, so f here going from x to y, and have a second map g going from y to z, then I can construct a new map g composed with f that goes from x to z by doing the following. I'd first take the function value of my input value x under f here, map it to y, and then the outcome of that I plug into g and map it to z. And the combination of the two gives me a new map, which I denote by this, which maps the value from x into z. And this is the composition of g and f. An important property of this composition is the associativity. So if I have three maps that I compose, assuming they all go from certain sets to other sets that it's even possible to compose them, then the composition of H with the composition of G and F is the same as the composition of the composition of h and g with f. And to see this, well, we simply apply the definition a few times. So we take any x from our input domain, plug it into this function, then by definition this is the same as h being applied to the value of x under the composition of g and f. And this inside here, inside the outer parenthesis, is the same as g being applied to the value of f of x. And to that we apply h. But this, by definition again, is the same as the composition of h and g being applied to f of x. And this again, by definition, is the same as the composition of h and g composed with f being applied to x. Let's look at examples again. So we can view the restriction as a composition of function f and an inclusion map. So f going from x to y and x0 being a subset of x, then we already learned that the restriction of f to x0 is simply, well, again, the map f, but we only plug in values coming from the subset f0, x0. And we can view this as composing f with the inclusion map. So the inclusion map from x0 into x just takes any element of x0 and maps it to itself, but this time considered in the bigger set x. And what comes out there we plug into f, and that's the same as the restriction of the map f to the subset x0. Any map can be composed with the identity maps. So if f is any map from x to y, then we have the identity on y composed with f is the same as f, and that's the same as f being composed with the identity on x. So composing with the identity maps doesn't do anything. We can compose rotations. Now assume r alpha and r beta are rotations by angles alpha and beta about the same center of rotation in the plane. That's important, they rotate about the same point. And then we can compose the two, so that amounts to first rotating by the angle beta and then rotating by the angle alpha about the same point. And geometrically it's clear that this is the same as rotating about the sum of the two angles. So the composition of these two rotations is actually the rotation by the angle alpha plus beta. And here's a bit more complicated example. So first we have the map f from the positive real numbers into the real numbers, mapping every value x to 1 over x. And then we have a second map from the real numbers again into the real numbers, g, which maps x to this quadratic polynomial expression, x squared minus x plus 2. And now the composition of the two goes from the positive real numbers to the real numbers, and from those again to the real numbers. And what happens here is we take g, but instead of plugging in x as its argument, we take the function value under f of x. So this map, this composition becomes x mapping to f of x squared minus f of x plus 2. So we take this expression but replace x by f of x. And now we can make f of x explicit. So this becomes 1 over x squared minus 1 over x plus 2. So this is the composition of the function f and the function g. Now another exercise for you. Pause the video for a few minutes and prove the following. F from x to y and g from y to z are maps. We assume that the composition g with f is surjective. That means all the elements of Z appear in the image of G composed with f. And then you should show that this implies that the map G is already surjective. Try this now, please. Okay, I hope you gave it a try. Now let's look at the solution. We pick an arbitrary element Z in the set big Z, and we want to show that for every such element there will be an element in Y such that G maps this element Y to our element Z. That would mean G is surjective. Now our assumption is that the composition GF is surjective, so by assumption there exists an element X in this set such that the composition GF applied to X maps to Z, and the composition is by definition just the same as G being applied to f of X. But of course here we see what's going on. There does exist some element Y in the set Y, namely f of X, that is mapped to Z by the function G. And this holds for all elements Z, so this means G is surjective. And here we move towards a different characterization of bijective maps. So we say a map F is invertible if there exists another map f to the minus 1 from y to x. So going the opposite way, if f goes from x to y, then the map f to the minus 1 goes from y to x, with the following property that f composed with f to the minus 1 is the identity on y, because here we plug in values from y first, and then we map them to x, and then going via f we map them back to y. And if nothing happens on this way, and also in the other direction nothing happens, so if we plug in a value into f, map it to y, then apply f to the minus 1 to this value and map it back to x, and if that composes to the identity on x, then we say that f to the minus 1 is the inverse map of f, and we say f is an invertible map. So this means we can undo the action of f via this inverse map. And somewhat loosely we also call f to the minus 1 just f inverse. And what's clear from this definition, if this inverse map exists, then it is also invertible, and its inverse is just the original function f. This just follows if you reverse the roles of f and f inverse in this definition. But beware, not always can you assume that such an invertible map exists. More precisely, a map f from x to y is invertible if and only if f is bijective. So these two mean the same thing, f being bijective and f being invertible. And we will prove this. And we have to prove an equivalence here, so we will prove it in 2 steps. First, I will assume that f is invertible and conclude that f is bijective. And in the next step, I will assume that f is bijective and then conclude that it has to have an inverse map. Okay, first the direction from here to here. Suppose f from x to y has an inverse, f to the minus 1 from y to x. I need to show that it's bijective, that f is bijective, so I need to show it's injective and it's surjective. So first I want to show it's injective. And to do this, I take 2 elements, x1, x2, from our input set x, and I suppose they map to the same value, f of x1 equal f of x2. What I want to show is that then x1 already has to be identical to x2. This would mean that f is injective, and that's my goal to show right now. So x1 is the same as identity x being applied to x1, but the identity x is the same as f inverse composed with f being applied to x1. And by definition of the composition, this is the same as f inverse being applied to f of x1. But here our assumption is that f of x1 is the same as f of x2. So this is the same as f inverse being applied to f of x2. And again, by definition of the composition, this is the same as f inverse being applied to f. F inverse composed with f being applied to x2. But this is the same as the identity on x being applied to x2, which is x2. So here, through this rather long chain of equalities, we see that x2 is identical to x1. So from the assumption that they get mapped to the same value under f, we conclude that they're identical. And that means f is injective. Now I will show that f is surjective, and together with the injective part, this means that f is bijective, which would conclude this part of the proof. So let y be any set in the codomain big Y, and to show that f is surjective, I need to show that for this arbitrary element I can find some element in x that maps to it. So y is the same as identity applied to y, and this is the same as f composed with f inverse applied to y, which is the same as f of f inverse of y. And this is an element in x, so there exists an element x, namely this particular f inverse of y, that is mapped to y under the map f, and this means f is surjective. And since it is injective and surjective, it means f is bijective, and we're done with the direction from the left to the right. Now we go the opposite direction. We assume f is bijective, and we want to show that it is invertible, so we have to give an inverse map for f. So it being bijective, it means that for every y in the codomain big Y, there exists some element x index y in the domain such that f of x index y is mapped to y. This follows from the surjectivity, and because it's also injective, this x index y is unique. So because this is unique, I can define a function or a map f bar from y to x, which maps y to this unique element x index y. And you might already suspect that this f bar will turn out to be our inverse map, but we have to verify this. So we look at f bar composed with f applied to any element x from the domain big X. By definition of the composition, this is just f bar applied to f of x. And by definition of f bar, this is just the element x index f of x. But if you look at how we defined these elements x index y, this is just x, because it's simply the element that under the map f gets mapped to f of x, and that's just x. So it follows that f bar composed with f applied to x is x, so it is the identity on x. And now we look at the other composition. For any input value y, f composed with f bar applied to y is f applied to x index y, because that's how we defined f bar. But f applied to x index y is simply y. So f composed with f bar is the identity on y, and those two together now imply that f bar is in fact the inverse function f to the minus 1 of f. And this means f is invertible. And this way we have concluded the direction of the proof that if f is bijective, it is invertible, and together with the other direction of the proof, this means we have established this equivalence. F being invertible and f being bijective means the same thing. Now be very careful. Many beginners confuse these notations. They confuse the inverse map of f with dividing by f. Now, of course, these are not the same, and in many instances for certain sets where we define f, this expression wouldn't even make any sense. But here's an example to explicitly show you that they're two separate things. So I look at the quadratic function from the non-negative reals into the non-negative reals. We already saw that this is bijective, and hence it is invertible. And the inverse map is given by the square root function, f to the minus 1 from the non-negative reals to the non-negative reals, mapping x to its square root. So f inverse of 2, for example, is the square root of 2. But f of 2 is 4, and 1 over f of 2 is 1 over 4, which of course is not the same as the square root of 2. Because, as we saw previously, the square root of 2 is not a rational number, but 1 over 4, of course, is a rational number. So these two expressions here are not the same. So be careful not to confuse that. Some other examples of inverse maps. So we look at the exponential map, which we haven't properly introduced in this course, but I hope you remember it from school. The exponential map takes real numbers and maps them to positive real numbers by taking the exponential of the Euler number e with x. And this one is invertible, and its inverse is called the natural logarithm, log, mapping positive real numbers into real numbers. And the rotation in the plane, so again r alpha is our rotation about an angle alpha around a certain center of rotation. A rotation is invertible simply by composing it with a rotation about the same angle but in the opposite direction, so with minus alpha. So we first rotate by minus alpha, and then we rotate in the opposite direction by plus alpha, and together it is as if nothing at all had happened. So this composition yields the identity r alpha minus alpha, which is r0, so just a rotation by an angle of 0. And that's of course the same as if we first rotate by plus alpha and then rotate back by minus alpha. Now another lemma with some small but very helpful properties. So if we're given an injective map f from A to B, then this injective map is actually bijective onto its image in B. So f from A to the image of f is bijective, and in particular we can form an inverse function from the image of f to A. And the second one is f from A to B and g from B to C. If they are injective maps, then their composition g after f is also injective. This is an injective map going from A to C. And we prove this. First, we assume that we're given this injective map f from A to B, and f from A to its image is always surjective. That's immediate from the definition of the image, because the image of f are just precisely the values in B that appear as values of this map f. So every one of them has a non-empty preimage. And since f is injective by assumption, it means that this map here is bijective. For the second part, suppose that we're given two elements A1, A2 in A, such that the composition G composed with F applied to A1 is the same as G composed with F applied to A2. And what we want to show is that then A1 and A2 must be identical. Now, this composition is just G applied to F A1, and this composition here is just G applied to F A2. Now we have assumed that G is injective, so by injectivity of G, this implies F of A1 is equal to F of A2, but we also assumed that F is injective. So the injectivity of F implies that A1 equal A2, and that is what we wanted to show. We have found that G composed with F is injective if G and F are injective. And finally, another exercise for you. Pause the video for a few minutes and prove the following. If F from X to Y and G from Y to Z are invertible maps, show that the composition G composed with F from X to Z is also invertible. And in light of theorem 22, this means that the composition of two bijective maps is again bijective, because bijective and invertible mean the same thing. Please give this a try now. Okay, let's look at the solution. So let's F to the minus 1 from Y to X and G to the minus 1 from Z to Y denote the inverses of F and G. And then I claim that the composition of the inverses is the inverse of the composition. So F inverse composed with G inverse from Z to X should be the inverse of G composed with F. Note that the order of F and G gets reversed when taking the inverse. And I can do this simply using the associativity of the composition. So I compose this one with this one. And because of associativity of the composition, I can put these two into parentheses, but then I know this is the identity on Y. So I can just leave this one out and arrive here. But then I know that this is the identity on X. And similarly for the other direction, if I composed G composed with F inverse composed with G inverse, I can move the parentheses to look at these two. These cancel out to the identity on X. So I can just drop this. Then I get G composed with G inverse, but this is the identity on Z because G was assumed to be invertible. And those two together simply mean that this is indeed the inverse of G composed with F, and that shows that G composed with F is invertible. And that's it for this lecture. Thank you very much for watching. It's been quite a long one this time, and please like this video and subscribe to my channel. And see you next time.